Hello everyone, good morning. Today I am going to discuss the second lecture of the welding metallurgy. So, the question number 6 is that we have to match the following. So, these three are the different polarities used in gas tungsten arc welding, and these are the different properties of them. So, the first is direct current electrode negative, second is direct current electrode positive, third is alternating current electrode. Okay, so in the first, let's see, these are the different polarities that is used. The first is the direct current electron negative. Okay, this is also called a straight polarity. This is also called a straight polarity, and this is the most common polarity in gas tungsten arc welding. Okay, electrode is connected to the negative terminal of the power supply, and electrons are emitted from this tungsten electrode and accelerated while traveling through the arc, and these accelerated electrons falls on the metal surface. Okay, and they produce heat here. Okay, one more term associated with that is work function. Now the work function is the amount of energy required for an electron to get emitted from that tungsten electrode, and when the electrode strikes the metal surface, strikes the workpiece, then the equivalent amount of energy is released here at the workpiece. Okay, so in that case of direct current electrode negative, we have deep weld. That is deep weld because the melting is taking place at the surface. Okay, and there is no surface cleaning. So the first will match with R, that is deep weld and no surface cleaning. Now coming to the next, let's see here. This is DCEP, that is the direct current electrode positive, and this is called a reverse polarity. Okay, so let's see here in the figure. This is the direct current electrode positive, and in that case electrode is connected to the positive terminal of the power source. This is the positive terminal of the power source. Heating effect of electron is now at the tungsten electrode. Here the electrons move from the specimen. Okay, the specimen emits the electrons, and this moves and strikes the tungsten electrodes here. So heating of the tungsten electrode takes place in DCEP, but in DCEN heating of a specimen takes place because the tungsten electrode emits electrons, and that electrons strike the specimen surface. Now this is just different of the opposite of the first one. Okay, so the heating effect is here, the melting is taking place at the tungsten electrode, hence in that case a shallow weld is produced. So this is shallow weld, there is no much deep welding. And next is that positive ions of the shielding gas, these are the positive ions of the shielding gas, gets bombarded at the workpiece. Okay, and it knocks out the oxides layer of the surface, and it produces a clean surface. So surface cleaning occurs in DCEP. So that is the shallow weld and surface cleaning. So shallow weld and surface cleaning, so it will match with P. Coming to the next, AC, and this is the alternating current. And this type of polarity, that is DCEP, direct current electrode positive. This polarity is used for the metals in which deep penetration is not required. Okay, when the welding does not require deep penetration, then we use DCEP. Okay, and it is very useful for the welding of metals which forms oxide layers, just like aluminum and magnesium. So in case of welding of aluminum and magnesium, we use DCEP polarity. Now coming to the AC, that is the alternating current, and it has reasonably good penetration and oxide cleaning action also. So in AC we can get both good penetration as well as oxide cleaning, and it is used for aluminum alloys, often used for aluminum alloys. So this is the correct match here. Coming to the next one. Now the problem is, select the corrective statement. First is, helium can be ionized easily than argon. Okay, we know that helium has the highest ionization energy in periodic table, and its ionization energy is 24.5 electron volt, and for argon ionization energy is only 15.7 electron volts. So helium has highest energy in the highest ionization energy in the periodic table. So it is very difficult to knock out electrons from the helium because there is a stronger force of attraction between the electrons, valence electrons, and the nucleus due to its small size and high Z effective. So helium is difficult to ionize, so this statement will be incorrect. Coming to the next. Argon offers more effective shielding than helium. So we know that argon is heavier gas and it is much heavier than helium, so it offers more effective shielding. This is absolutely correct. With DCEP and AC, helium has greater oxide cleaning action than argon. Again, we know that argon is heavier than helium. Okay, so argon will clean the oxide more effectively than helium. So due to its large molecular weight, argon has better oxide cleaning action as compared to helium. So this statement is absolutely incorrect. Now, argon is better than helium for gas tungsten arc welding. Okay, now argon has higher molecular weight, so it can have greater oxide cleaning ability as compared to that of helium. Okay, and it has also low ionization potential. Okay, so it can be ionized very easily. So there are lot of advantages of using argon over helium. These are: argon has low ionization potential, that is low ionization energy. Second is, if the ionization energy is low, then there will be low voltage drop across the arc. So in case of argon, the voltage drop across the arc will be low as compared to helium. Again, the more effective shielding will be done by argon because of its higher molecular weight. Okay, and it also has greater oxide cleaning action. And one more important thing is that argon is cheaper than helium. Okay, so the cost of argon is much lower than helium. So again, all this make better than helium for the gas tungsten arc welding. Now coming to the next. GTAW, that is the gas tungsten arc welding, can be used to weld titanium, zirconium, aluminum and magnesium. Okay. Since we know that gas tungsten arc welding is one of the cleanest arc welding, that is the cleanest arc welding, okay, and hence it can be used for the welding of reactive metals like titanium, zirconium, aluminum and magnesium. These are very reactive metals and they can be welded by the gas tungsten arc welding because this is the cleanest arc welding. So this is absolutely correct. Now coming to the next problem. Select correct statement. Okay, about gas metal arc welding. Okay. Now we have to select the correct statement about the gas metal arc welding. Now the first statement, it is also known as MIG. Okay. So we know that gas metal arc welding uses inert gas like argon, helium. Hence, it is also known as metal inert gas welding, that is MIG. So this is absolutely correct. Coming to the next. Shielding gases are argon, helium, that is inert gas only. This is not correct. MIG uses inert gases like argon, helium, okay, that is used for the welding of aluminum alloys and stainless steel and alloy steel. It also uses carbon dioxide for the low carbon steel and mild steel. Sorry, medium carbon steel. For low carbon steel and medium carbon steel, it uses CO2 gas. Okay, so this is incorrect that MIG only uses inert gas. This statement is incorrect. It uses inert gas as well as CO2 that is not inert in nature. Coming to the next. DCEP is preferred over DCEN and AC. Okay. The third is that DCEP is preferred over DCEN and AC. Okay. Unlike gas tungsten arc welding, okay, we use DCEP, that is the direct current electrode positive, in MIG welding. Okay, because it produces more stable arc, a smooth metal transfer with low spatter loss and good weld penetration. So this statement is absolutely correct that in case of MIG we use direct current electrode positive polarity because it produces a stable arc, a smooth metal transfer with low spattering of metals and good weld penetration. Coming to the next. Gas metal arc welding is preferred over gas tungsten arc welding for welding of thicker workpiece. Okay. Gas metal arc welding has much higher deposition rate. The deposition rate is much higher than gas tungsten arc welding, and hence if the deposition rate is higher, then it can be used for welding of thicker workpiece. So this is absolutely correct. Now coming to the next. Select the correct statements. First is, no shielding gas is needed for submerged arc welding. Okay. In submerged arc welding, that is SET-2. Okay, that is SET-2. Short form is SET-2. So in submerged arc welding, arc is shielded by a molten slag and granular flux. So here arc is completely submerged and invisible, so no shielding gas is required. Okay, because the molten metal is separated from the air by molten slag and granular flux. So this statement is absolutely correct. Now, submerged arc welding greater than gas metal arc welding greater than gas tungsten arc welding, that is the thickness of the workpiece to be welded. So we know that the thickness of the workpiece to be welded is directly proportional to the deposition rate, and we know that this is the order of deposition rate, and in which electro slag welding has the highest deposition rate, and after that submerged arc welding, then fluxed core arc welding, then gas metal arc welding, then gas tungsten arc welding. So SAW, GMAW here, and GTAW. So this is absolutely correct, and this is a fact. Okay, coming to the next. This is the rate, deposition rate. Again, this is absolutely correct. In electron beam welding, thermoionic emission of electron takes place. Okay, so in electron beam welding, cathode of electron beam gun, that is negatively charged filament, and it is heated up to its thermoionic emission temperature, and then this filament emits electrons which are accelerated by the electric field between the negatively charged electron and positively charged anode, and further they fall on the workpiece surface. So this is absolutely correct that in electron beam welding, thermoionic emission of electron takes place. So now coming to the question number 10 here. Now, the statement here is, the first statement here is, we have to select the correct statement about the electro beam welding, that is EVW, that is the electron beam welding. Okay, so the first statement is that, in that case, is that electron beam welding is greatly dispersed at low ambient pressure. So let's see here, these are the dispersion of the electron beam at a different pressure. The first, this is at the 750 torr pressure, this is at the 500 torr, this is at the 250 torr, this is at the 50 torr, and this is at the 5 torr. So we see that as we decrease the pressure, okay, the dispersion of the electron beam decreases. Okay, so electron beam is greatly dispersed at low ambient pressure. This is absolutely incorrect. If the pressure is low, then the dispersion of electron beam will be low. So this is incorrect. So as we increase the pressure, like in case of 750 torr, there was a high pressure and there was greater dispersion of the electron beam. Coming to the next, it can vaporize the metal and produce a deep penetrating keyhole. Okay, so as we know that electron beam can be focused in a very low diameter range, that is 0.3 to 0.8 millimeter. Hence it has very high power density, and the power density is in the range of 10⁻10 watt per meter square. So this is a very large power density, and hence this high power density makes it possible to vaporize the metals and produces a deep penetrating keyhole. So this is absolutely correct. Coming to the next, energy required per unit length in electron beam welding is more than gas tungsten arc welding. Okay, so this is absolutely correct. Then energy required in electron beam welding is very low, that is 1.5 kilojoule per centimeter. But in case of gas tungsten arc welding, it is about 22.7 kilojoule per centimeter. Okay, so the energy required per unit length in electron beam welding is very low as compared to that, because of very high power density in case of electron beam welding. But in case of gas tungsten arc welding, the power density is not much, and hence there is very high heat losses, so it requires high energy, okay, energy density. So this statement, that is the C, is absolutely incorrect, because the electron beam welding requires low energy. Coming to the next, it is not desirable for rimmed steel. Okay, so we know that rimmed steel is incompletely degassed steel. So during electron beam welding under high welding speed, the gas bubbles that comes out of the rimmed steel do not get enough time to leave the deep weld pool. So it causes weld porosity. So the gas that comes out from the rimmed steel does not get enough time to escape, because the welding speed of the electron beam welding is very high. So this is not desirable for rimmed steel. This is absolutely correct. Coming to the next, electron beam welding can be used for magnesium alloys and PB containing alloys, that is the lead containing alloys. So we know that magnesium and PB lead has very low melting and boiling point, so they can easily get vaporized, and their vapors can fall the pump and contaminate the vacuum system of electron beam welding. So this is incorrect, because in electron beam welding is done in vacuum to avoid the dispersion of the electron beam, because in the previous question we have seen that if the pressure is high, then there is more dispersion of electron beam, and if the pressure is low, then the dispersion of electron beam is very low. So for better welding, we use vacuum in case of electron beam welding. Coming to the next, it involves narrow heat affected zone, and this is absolutely correct, because in case of electron beam welding, you can see this is the keyhole, deep penetration, and hence it will have very narrow heat affected zone. Coming to the next, select the correct statement about laser beam welding. Okay, so this is the problem that has been asked here, and we have to select the correct statement about the laser beam welding. Okay, that is LBW. Okay, first is yttrium aluminum garnet, that is YAG laser, is doped with neodymium. So laser beam welding uses laser produced by the solid state laser or gas laser. Okay, solid state laser is a single crystal doped with a small concentration of the transition metal of rare earth element, and in yttrium aluminum garnet this is doped with neodymium. This is absolutely correct. Coming to the next, gas laser uses mixture of CO2, N2 and helium. Again, this is absolutely correct. So CO2, N2 and helium gas mixture is continuously excited in laser beam welding. This is correct. Surface modification like roughening, oxidizing and coating reduces reflectivity. Okay, reflectivity. So in laser beam welding, reflectivity is a major problem. So if the metal surface is shiny in nature, so it can reflect the laser beam. Okay, so laser beam welding, reflectivity is one of the problem here. So about 95% of the CO2 beam power can be reflected by a polished metal surface. Okay, so if we want to decrease the reflection of the laser beam, then we have to make the surface rough and hard. So making the surface rough, we can increase the absorption of the laser beam, and in that case keyhole can be easily formed, and once the keyhole is established, then absorption is very high because the beam is trapped inside that keyhole by total internal reflection. So this is absolutely correct. Now coming to the next, helium is preferred over argon for shielding in laser beam welding. Okay, as we know that helium has greater ionization energy, that is 24.5 electron volt, and in case of argon it has lower, that is 15.7 electron volt. So argon can easily be ionized because it has 15.7 electron volt ionization energy, that is much lower than that of helium. So it is better to use helium as a shielding gas, but actually we don't use the pure helium. In that case we use helium plus 10% argon by volume, because helium is very, its molecular weight is very low, that is it is very lightweight gas, that's why it does not shield effectively. So we use a mixture of helium plus 10% argon so that its shielding capability increases. So this is absolutely correct. So all of these statements about the laser beam welding are correct. So coming to the next problem here. So let's see, this is the next one, and in that case let's see what is the problem here. If a current is increased 2 times and the duration is reduced by half, keeping other parameters unchanged, then the order of change in the heat generated in a welding process H. Okay, so we know that heat generated in the welding process is given by H equal to I square R into T, that is the heat generated, that is the current, resistance and the time. So in the first case, let H1, that is I1 square R into T1. Okay, in case of H2, the second heat generated, so in that case the current is made 2 times, so this will be 2I1 square into R, and other parameters keeping unchanged, so this will be T1 again. And if we find H1 by H2, we will get this RT1 will be cancelled out. Okay, that will be 1 upon 4 1 square I1 square, this will be 2I1 upon 2I1 squares, that will be the correct one. Now H1 upon H2, will be equal to here sorry, there is a mistake here. Sorry, let's try again. This is the formula for heat generation, that is H square H equal to I square RT. So in the first case, let current is I1 square into R into T1 duration. In the second case, current is made 2 times, so this will be 2I1 square into R, and duration is reduced by half, so the time will be T1 by 2. And now if we find H1 by H2, then we will get 1 upon 2. So H2 will be equal to 2H1. So in that case, heat generated will be the 2 times of the previous one. So in that case, heat generated will be 2 times as compared to the previous one if we increase the current 2 times and decrease the duration by half. Okay, coming to the next problem here. This problem has been asked in GATE 2006, and the question is, in submerged arc welding, a heat input of 4 kilojoule per millimeter is used. Okay, now if welding speed is doubled, then welding heat input will be, okay, increases by a factor of 2, remains unaffected, decreases by a factor of 2, increases by a factor of 4. So if we increase velocity by a factor of 2, then the distance covered will be doubled. Okay, so heat input will be half of the previous one. This is very simple. If you increase the velocity by a factor of 2 less, this is the distance covered in velocity v, and if you increase the velocity, then if you make 2v, then in the same duration t, it will cover 2d of distance of length 2d, and in that case heat input will become half of the previous one, because this is distributed upon this distance and this q is distributed upon 2d distance, so the heat input will be the half of the previous one. So the correct option is decreases by a factor of 2. Now coming to the next problem here. Now we have to select the correct variation of grain size. This is the weld and this is the heat affected zones. Okay, these are the points 1, 2 and 3. We have to just select the correct graph according to this. Okay, so we know that closer the fusion boundary, this is the fusion boundary. Okay, closer the fusion boundary, higher is the temperature. This temperature, that is T1, is the highest, T2 is lower than T1 and T3 is even lower than T2. Okay, so closer to the fusion boundary, higher is the peak temperature. Okay, and materials will stay longer at higher temperature. As we know that grain growth increases with annealing temperature, so if the temperature T1 is higher, then here the grain growth will takes place more as compared to 2, hence the grain sizes will be more at 1. As we move in that direction, the grain sizes decreases. Okay, so grain growth, as we know that grain growth increases with the annealing temperature, so grain that is close to the weld or the fusion boundary will have larger size. So one has the largest grain size, so in that case one has lowest grain size and 3 has the largest. This is incorrect. This one is correct. So as we move away from the fusion zone, then the grain size decreases. This is absolutely correct. Coming to the next. Select the correct statements, and we have to select the correct statement. Let's see the first statement here. In electron beam welding, very little recrystallization is observed in heat affected zone of work hardened material. So we know that in electron beam welding, due to very high power density, the heat input is very low, okay, and the cooling rate is also very high in electron beam welding. So very little recrystallization is observed. This is absolutely correct, and this is due to low heat input and high cooling rate. Coming to the next. In gas metal arc welding, recrystallization and some grain growth in hatch heat affected zone is observed. This is absolutely correct, because in that case heat input is higher and the cooling rate is lower, so a lot of time here the crystallizing grain gets a lot of time to crystallize, and hence grain growth and recrystallization appear significantly in gas metal arc welding. So this is due to high heat input and low cooling rate. But in case of electron beam welding, the heat input is low as well as the cooling rate is very high. So in that case, very little recrystallization is observed. But in gas tungsten arc welding, appreciable and significant recrystallization and grain growth in heat affected zone is observed. Coming to the next. For better resistance welding, metal should have high thermal conductivity. No, absolutely incorrect. Because if the thermal conductivity of the metal would be higher, then there will be lot of heat losses due to the conduction. Okay, so for better electrical resistivity, because in resistance welding we should have, the material should have higher electrical resistivity, low melting point and low thermal conductivity. So this is absolutely incorrect. Coming to the next. Titanium 3 oxide in heat affected zone in high strength low alloy steel increases the toughness of heat affected zone. So titanium 3 oxide is very stable oxide and it does not dissolve even at high temperature. So basically it do not stop grain growth because it does not get dissolved in the molten metal. Hence it only acts as an effective nucleoside, okay, for the nucleation and formation of acicular ferrite. Hence acicular ferrites forms within the coarse gamma grains, and hence it improves the heat affected zone toughness. So Ti2O3 does not get dissolved, hence it acts as a nucleating site, that is the heterogeneous nucleating sites, and where acicular ferrites nucleates in the gamma phase, and that acicular ferrites is responsible for better toughness of heat affected zone. So this is absolutely correct. Coming to the next. Now we have to match the following. The deoxidizers are the metals which have metals or non-metals which have very high affinity towards oxygen, and these are aluminum, titanium, magnesium. These are acting as a deoxidizer. Now Second is grain refiner. Okay, so the grain refiner that refines the grain, okay, are generally the carbides and nitrides, that of niobium, vanadium and titanium, and in which TIN, that is the titanium nitride, is the most effective. Okay, so because the TIN has very low TIN has very low tendency to decompose and it dissolves at high temperature. So it is most effective in limiting grain growth in welding. So grain refiner matches with B. Now coming to the arc stabilizers. Arc stabilizers are the compounds that are used to stabilize the arc. Okay, they helps to maintain a stable arc. So arc stabilizer is ionic compound. Okay, as we know that arc is a ionic gas, that is plasma, that conducts electric current, and the arc stabilizer compounds, that are the ionic compounds, they decompose and forms ion that increases the electrical conductivity of the arc. So this, that is the potassium oxalate, lithium carbonate, potassium oxide, sodium oxide, they can easily decompose into ions and they increase the electrical conductivity of the arc. So it helps the arc to conduct electric current more smoothly. So it will match with this. So this is the end of the second lecture for the welding metallurgy. Thank you very much and all the best for GATE 2018. Thank you.